Welcome everybody, Math 104, we're working on section 6.5 today, applications of rational expressions. So we're going to be working on some word problems today. We're going to start off with applications involving proportions. So with these, they're all set up the same way. There are four quantities, three of which are known, one is unknown. And we're going to take those four quantities and put them into a proportion. Now we need to set up these proportions so that we set up our ratios or rates consistently. So let's take a look at the first example. We've got a 20-pound bag of grass seed that costs $4.60. Okay, so those two quantities are connected to each other. 20 pounds and $4.60. And I've got two other quantities. How many pounds of grass seed? So we have an unknown quantity of grass seed, and we're going to declare a variable for that. It can be purchased for $11.50. So there's the cost of the unknown quantity of grass seed. I'm going to set up a proportion to solve this. I'm going to put 20 pounds. And notice I'm including the units when I set up the proportion. This is absolutely essential. You must include units. So we got 20 pounds for $4.60. So there's a rate. And one way to do this is to put that into one fraction. Now when we set up the other fraction, we have to do it in the same way. Pounds on top, dollars on the bottom. It's got P pounds on top, and the price of that is $11.50. All right, now we've got in both fractions, pounds on top, dollars on the bottom, so we have set it up correctly. And now we're going to solve, so we cross multiply. We can do $11.50 times 20 equals 460p. All right, 20 times 11.5, that's going to give us 230 equals 4.60p. Now we'll divide by the coefficient, divide by 4.6, and that gives us p equals 50 pounds. And just put a little description, make sure you include the units and what we're talking about, pounds of grass seed. Your turn, number one. If the correct dose of an antibiotic for an 180-pound person is 15 milligrams, find the correct dose for a 150-pound person. So this is a very common calculation in medicine. There are a lot of medicines that are where the dose depends on the weight of the person. So let's get our two connected quantities here, 180 pounds, 15 milligrams. Then the other person is 150 pounds, and we want to know how many milligrams to give them. So there's going to be our variable. All right. These two connected quantities, I'm going to turn that into a rate, 180 pounds over 15 milligrams. And on the other side, we got 150 pounds that will also go on top. So we're consistent. And then milligrams, I'll call that D for dose, milligrams. All right, there's our proportion all set up with units. Now we will cross multiply. D times 180. Now once you start doing the math, don't write the units down here. We only write the units in our initial proportion and the answer. They'll just get in the way when we're solving. All right, now on the other side we got 15 times 150. 2250. Okay, 180 equals 2250. Divide by 180. 180, and we get D equals 12.5 milligrams of the antibiotic. So that would be the dosage for a 150-pound person. Now sometimes these proportion problems are expressed a little bit differently. One of the quantities in the problem may require an expression instead of just a single number or a single variable. So a car with 8 gallons of gas remaining in the tank can travel 220 miles. So 8 gallons, 220 miles. So there's two connected quantities there. How many additional gallons of gas does the car need to travel 275 miles? Additional is the key word there. Additional means over 8. So we can write that as 8 plus G, the number of additional gallons we need over 8. Because we want to drive more than 220 miles, we want to drive 275 miles. And if 8 gallons will get us 220 miles, then we need some more gallons to go 275 miles. So when asked for how many additional miles, how many additional gallons, it's asking for how many gallons over 8. So that's the expression we need, 8 plus G. Now we can set a proportion with these. All right, these two quantities are connected, so we get 220 miles over 8 gallons equals 275 miles over 8 plus G. Now we'll cross multiply to solve. 220 times 8 plus G. Make sure to put parentheses around 8 plus G so we distribute in. And then 275 times 8. All right, now we can distribute in. Here we get 1760 plus 220G equals 275 times 8 gives us 2200. All right, we'll subtract 1760 from each side. That gives us 220G equals 440. Divide by 220, and G equals 2 additional gallons of gas. So this is an example of defining a quantity in terms of a variable. And that's a very important skill in math. Let's work on that in your turn number 2. An investor owns 80 shares of stock and earns a dividend of 280. So the idea behind dividends is that when you own a share of stock, the company then pays you a little bit of money for every share that you own. So the two connected quantities, 80 shares for $280. Now let's say that investor wants a dividend of 448 instead. How many additional shares of stock must the investor purchase? So here we got 448. Now how many additional shares? In addition to the 80 that this investor already owns. So we need 80 plus, and use S. All right, I usually try not to use S as a variable, but it just makes too much sense here. Because it kind of looks like a 5, but if we're careful about how we write it, we can get through it. Okay, so we use these 4 quantities then to create proportion. So these two quantities are connected, so we'll go $280, 80 shares, abbreviate with SH, that's fine. And then over here, we want $448 and 80 plus S shares. All right, there's everything with units. Now we can cross multiply. 80 times 448 equals 280 times 80 plus S. All right, now multiply and distribute. So we got 35,840 over here equals 280 times 80, and we get 22,400 plus 280S. Okay, so we're going to solve for S. Subtract 22,400 from each side, and that gives us 13,440 equals 280S. Divide by 280, and S equals 48. Additional shares of stock. Next up, we're going to look at some classic problems called distance rate times problem. Distance rate time problems. All right, here's the dirt equation. Distance, rate, time. Rate is just the speed. And we're going to look at current problems. So currents, either in water or air, affect the speed of travel. Speed is measured usually relative to something that is not moving. So if you look at the speed of the boat, we're going to measure that relative to the shore. If you want the speed of an airplane, you can measure that relative to the ground. So the current affects the speed, and if we're going with the current, traveling in the same direction as the current's going to speed us up. If we're traveling against the current, it's going to slow us down. Now, what we're going to do is kind of an idealized version of what actually happens in the real world. We're just going to take the current and either add it directly or subtract it directly from the speed. In the real world, it's usually kind of a percentage of the current that's added or subtracted from the speed, because not all of the speed of the current is transferred to the boat or the plane. Okay, so let's say we have a boat traveling at 20 miles per hour relative to the shore, and that's how fast it goes in still water. Water's not moving at all. If there's a 5 mile per hour current, then we have to either add or subtract that from the speed. So with the current, we take the speed in still water, 20 miles per hour, and add the speed of the current. All right, still water and current. And then against, it'd be 20 minus 5. So this boat would be going 25 miles per hour with the current, or 15 miles per hour against the current. So let's apply this concept to the following example. A small fishing boat travels 36 miles against the current. In the same time, travels 44 miles with the current. If the rate of the boat in still water is 20 miles per hour, find the rate of the current. Okay, step one. We want to locate the quantity we're solving for. This will be our variable. The question asks for, find the rate of the current. So that's our variable. Rate of the current, I'm going to call that C. I don't want to call it R because we're already using R in the dirt equation. Don't repeat variables unless they refer to exactly the same thing. So C is the rate of the current. All right, now we're going to write expressions for the speed of the boat with and against the current. Given that the speed in still water is 20, so with current and against current. There's our two situations. With the current, starting with 20 miles per hour, and we're adding the speed of the current, which we've defined to be c. Against the current, the speed is 20 minus c. Okay, so there's the speed of the boat. Now, we're going to use the dirt equation, and we have two different situations. We're going to use two different dirt equations. One for with the current, one for against the current. So D equals RT here, and D equals RT here. Now we plug in what we know. With the current, traveled 44 miles. So here's the D for with the current, 44 miles. The rate, we just found that, it's 20 plus C. And then T for the time it takes it to go that distance. Now against the current, we're given that we traveled 36 miles. So this D is going to be 36. The rate here is 20 minus C. And time is T. Now notice we used the same variable T in both of these equations. Now I just said don't repeat variables. But this T refers to the exact same time. It says in the problem, a small fishing boat travels 36 miles against the current in the same time it travels 44 miles with the current. So those T's are equal to each other. So we can use the same variable. And we're going to use that fact then to solve these. The fact that those T's are equal is really important. So let's solve each of these equations for T. So I'm going to divide by what T is multiplied by, which is 20 plus C. Divide both sides of the equation by 20 plus C. And we get T equals 44 over 20 plus C. And on this side, when we solve for T, divide both sides by 20 minus C. And we get T equals 36 over 20 minus C. And here's where the fact that the T's are equal to each other becomes so important, because now that's going to allow us to solve this. If T equals T, and T equals this over here, and T equals this over here, that means by the transitive property, these two things must be equal to each other. So we're going to set 44 over 20 plus C equal to 36 over 20 minus C. Now I've got a proportion, so we can cross multiply and solve. 44 times 20 minus C equals 36 times 20 plus C. And now we can distribute. 440 times 20, that gives us 80. Oops. And then 44 distributed to the second part here is negative 44C. And on the other side, we got 36 times 20. So that's 720 plus 36C. Now solving for C, I'm going to add 44C to both sides. And then subtract 720 from each side. And that gives us 160 equals 80C. Divide both sides by 80, and we get C equals 2. So let's describe what that is the current, and the units are miles per hour, so the current is 2 miles per hour. It's a good idea to check work at this point. So what we could do is plug in 2, find the rate with the current, so 22 miles per hour with the current, and 18 miles per hour against the current. And then just make sure we get the same time when we plug those in, and that'd be a good check. Your turn, number 3. Plane travels 100 miles against the wind in the same time it takes to travel 120 miles with the wind. The wind speed is 20 miles per hour. Find the rate of the plane in still air. So the question asks for find the rate of the plane in still air, so I'm going to define a variable for that quantity. All right, just like we did over here, we're going to do one part with the current, one part against the current. So we got the rate of the plane in still air, and we want to find the speed with the current and against the current. So we started, when we set these up, we started with a rate in still air. That was given in the problem in the last one. But here it's a variable. So both of these expressions are going to start with P, the rate of the plane in still air. And then we'll modify that with the current. The current is 20 miles per hour. So with the current, we add 20. And against the current, subtract 20. All right, so there's the speed. Now we're going to use the dirt equation. And plug in the values. Plane travels 100 miles against the wind, so against the current. So that's our distance, 100. And over here, it's 120 miles with the wind, so 120 over here. The rate, we just found that, P plus 20 times T. And over here is P minus 20 times T. And just like in the last problem, it takes the plane the same amount of time to do each of these. So those T's are equal to each other. So we're going to solve for T. Divide by P plus 20, and we get 120 over P plus 20. And on this side, we got T equals 100 divided by P minus 20. All right, since these times are equal to each other, these expressions are equal to each other. So we'll set them equal. Now we get a proportion, we can cross multiply and solve. 120 times P minus 20 and 100 times P plus 20. Distributing. So it gives us 120p minus 2400 equals 100p plus 2000. Solving for p, we'll subtract 100p from each side. That brings the p's to the left, so we get the numbers to the right. Add 2400. And we got 20p equals 4400. Divide each side by 20. And the speed of the plane in still air is 220 miles per hour. All right, next up, another classic problem known as the work problem. Reggie and Pat are raking leaves in their large yard. It would take Reggie 9 hours to complete the job working alone, and it would take Pat 6 hours to finish working alone. How long would it take to complete the job working together? All right, so we're not going to think in terms of how long will it take them to complete the job. Let's think in terms of what fraction of the job can each person complete in 1 hour. So if it takes Reggie 9 hours to complete the job, that means every hour Reggie gets 1/9 of the job done. So Reggie 1/9 of the job per hour. And for Pat, 1/6 of the job per hour. Okay, so that's how much they can do in 1 hour. Now I want expressions for how much they can complete in some number of hours. And I'm going to call that number of hours H. H represents the number of hours they're working. So multiply the fraction of the job that each person can do per hour by the number of hours. So for Reggie, that is H over 9, and for Pat, that is H over 6. Okay, now we know they're working together, so we want to combine their efforts together. All right, so this is what fraction of the job that Reggie can get done in H hours. And we'll add Pat, number of the fraction of the job that Pat can get done in H hours. Now when we add these together, how many jobs are they trying to complete? How many yards do they have to rake? Well, it's just one. So adding together the fraction of the job that Reggie can do, the fraction of the job that Pat can do, add those together should equal 1 job because they're raking 1 yard. All right, now we can solve this for H. So I want to get rid of these fractions. So I can multiply by 18 to get rid of the fractions. We're multiplying by the least common multiple of the denominators. So 18 divided by 9 is 2. So we have 2H here. And 18 divided by 6 is 3. So we have 3H here. And then continuing distributing over here, we got 18 on the right. So that gives us 5H equals 18 divided by 5. And we get H equals 18 fifths. So that's 3.6 hours, somewhere around there. Yeah, 3.6 hours or 3 hours and 36 minutes for them to rake the entire yard working together. All right, so let's use this idea of going from how long it takes them to complete the job to fraction of the job per hour. Let's use that technique to do your term number 4. So Stan can do the dishes in 45 minutes, while it takes Bobby 30 minutes. How long will it take them working together? We'll define T to be the time to complete the dishes, just like we defined H to be the hours working. All right, Stan can do the dishes in 45 minutes. So each minute, Stan does 1/45 of the dishes. Bobby, it takes Bobby 30 minutes to do dishes. Bobby does 1/30 of the dishes per minute. All right, so we're going to multiply by the time, measured in minutes. Should put the units there so we know what we're measuring it. So for Stan, then, this becomes T over 45. And for Bobby, this becomes T over 30. Now they're working together, so we want to add the work that Stan does to the work that Bobby does. So that's T over 45 plus T over 30 equals 1 job. Now, the least common multiple of 45 and 30 is 90, so we're going to multiply this entire equation by 90. 90 divided by 45 is 2, so we get 2t there. 90 divided by 30 is 3, so we get 3t equals, distributed in here, we get 90. So 5t equals 90 when we combine like terms. Divide by 5, and we get t equals, like 18, not 14. So t equals 18. So it takes them Takes them 18 minutes to complete the dishes. Now this last one, this one is fairly tricky. It's a whole new level in mathematical modeling. It's good to have a challenge here at the end. Your turn, number 5. James and Sarah are driving from Atlanta to Jacksonville, the distance of 310 miles. I find it very, very helpful to draw a little diagram of what's going on. So we got Atlanta and Jacksonville. Make sure I don't do that. Okay, so we're driving from Atlanta to Jacksonville. And that is 310 miles. So 310 total. James, whose average rate is 5 miles per hour faster than Sarah's, will drive the first 130 miles of the trip. So here we got 130 miles, and this is Jack. And then over here, the rest of the way, 310 minus 130 is 180. So that means Sarah is driving 180 miles. The total driving time is 5 hours, and we're going to determine the average rate of each driver, keeping in mind that James is going 5 miles per hour faster than Sarah. So I'm going to define a variable for Sarah's rate. And define a variable h. That's how fast Sarah is going. We know that James, whose average rate is 5 miles per hour faster than Sarah's, so we can use this to write an expression for James's rate. So he's 5 miles per hour faster, so h plus 5. All right, so there's the rates of the two drivers. The total driving time is 5 hours. So I'm going to find this variable j for James's time. Now, if the total time is 5 hours and James's time is j, what's Sarah's time? Right? From here to here is 5 hours. James took up j hours, so we take the total time 5, subtract j, and we get Sarah's time. So that'd be 5 minus j. All right, there's some expressions we can use then. And we know we're still going to use the dirt equation, so we need a dirt equation for both of these legs. D equals RT and D equals RT. Now we know the distances, we're given those, so I can plug those right in. 130 equals, and now we have to use our expressions. All right, this is, did I say Jack? I don't know where I got Jack from. This is James. Jack's not coming on the trip. Okay, D equals RT. Now we know James's rate is h plus 5. And we know James's time is j. So we get h plus 5 times j on the right. Now we'll do the same thing for the right equation. I'm going to move this over a little bit. The distance is 180 for Sarah. Sarah's rate, h. And Sarah's time, 5 minus j. And now we have 2 equations and 2 unknowns. So it's going to take some work to solve those. So I'm going to solve for one of these variables and then substitute. So I'm going to go ahead and solve for j here. So j equals, if I divide both sides by h plus 5, we get 130 divided by h plus 5. And now we can go over here and substitute in for j. So that gives us 180 equals h times 5 minus, and take this, plug it in here. 130 over h plus 5. All right, so we got the same equation there, just with j substituted. And now we're down to an equation with one variable in it. So we can solve this for h. All right, so I'm going to distribute h in. All right, h is distributed into 5, and then multiply it by the numerator to get 130h over h plus 5. And now, got this fraction there. That's a problem. Let's get rid of that. I'm going to multiply this entire equation by h plus 5. And that's going to eliminate the fraction. So I just need to distribute in. So h plus 5 times 180, that gives us, and I'll just do the distribution on the next step. And we'll have the same thing here. We'll do 5h times h plus 5. And then here the h plus 5's cancel, leaving just minus 130h. All right, now we're down to just a basic linear equation. So we can distribute in. So it gives me 180h plus 180 times 5 is 900 equals 5h times h, which is 5h squared, plus 25h minus 130h. All right, now let's get everything to one side of the equation. Well, this is going to go here. All right, so we got 5h squared. Combine these and subtract 180. That gives us negative 285h minus 900. Okay, now we need to factor and solve using the techniques from chapter 5. So whenever we're factoring, what's the first thing we do? Take out the GCF. So that gives us 5 times h squared minus 57h minus 180. Now, since we're set equal to 0, we can just divide both sides by 5 and get rid of that 5. So we just get 0 equals h squared minus 57h minus 180. And this is a very difficult factoring problem. That factors into h plus 3 times h minus 60, and then solving each of these individually, we get h equals negative 3 and 60. So what do we just find? H, we defined h to be Sarah's rate. So that means Sarah drove at 60 miles per hour. And we know that James is 5 miles per hour faster. So James drove at 65 miles per hour. All right, so that's a tough one, especially when they have to define 2 different variables, set up 2 equations, solve a system of equations. So that's the next level in word problems. That's it for today, and that wraps up Chapter 6.